I'm Huijie Chen from Beijing Institute of Technology, and I will present our work. Listen to your fingers. Use authentication based on geometry biometrics of touch gesture. People always use the smartphone to store your personal information and online payment. To prevent the smartphone to be accessed by strangers, many user authentication methods are designed, such as facial recognition, fingerprint, and passcode. In contrast, the passcode is convenient, low hardware cost, and very comfortable, and more users like it. However, passcode becomes less reliable because it is highly possible to be inferred by many such channel attacks. Of course, many effort has been made to provide additional verification for passcode. For example, the behavior biometrics and geometry constraints between fingers are used for authentication. However, they are always less accurate or has limited scenario. These limitations motivate us to design a reliable second-factor user verification for passcode. We observe that when input a passcode, the user hand posture is diverse, and the hand geometry has individual difference. Besides, the hand posture spatial feature can be extracted from the acoustic multipath signal. We will use acoustic sensing to scan the user's hand posture and extract the spatial pattern for authentication. Three challenges need to be addressed: how to get the acoustic fragment when the fingers stop at some landmark positions, how to extract the fine-grained multipath features, and how to design a secure authentication method with limited samples. The system overall comprises of three components: acoustic signal segmentation, hand geometry, biometrics profiling, and authentication model. To get the acoustic fragment, we estimate the finger static appearance with the finger trace data and determine the start time in the acoustic signal based on the typing sound event. The sampling frequency of the finger trace is not consistent. Therefore, we first use the linear interpolation method and then calculate the slope and detect this red point. For the acoustic signal, we use a bandpass filter to remove noise, to extract the envelope, and search backward from the first peak to locate the typing sound. We rely on the autocorrelation characteristics of the DC sequence to extract the fine-grained multipath feature. This finger is an example of this sequence. It needs to be modulated into acoustic signal for active acoustic sensing. First, we increase the sampling rate in the frequency domain, then make it audible for human by introduce a carrier signal FC. To get the multipath response, circle cross correlation is used for each acoustic fragment. Only the part near the direct path response will be used for feature extraction. The authentication model comprises of two stages: register stage and verification stage. In the first stage, the personal feature is generated. We align the samples and generated the occupancy map. And in the verification stage, once the user input a sample, the similarity will be calculated for user authentication. And there are 30 volunteers participants in our experiment, and the evaluation is performed in 3 types of experiment. First, we study overall performance of our system. The average authentication accuracy is higher than 19%. We also evaluate the reliability of our system against the replay attack and the observe and imitate attack. This result shows that our approach can effectively resist these attacks. Our work targeted to provide a second-factor verification for passcode-based authentication method. It relies on the biometrics related with the touching gesture 3D shape and robust to the touch behavior variability. We use active acoustic sensing to extract the unique spatial pattern from the multipath signal for user authentication. The challenges contains acoustic signal segmentation, touch posterior biometrics profiling, authentication model. The evaluation shows it can effectively resist many attacks, such as replay attack and adversarial imitate attack. That's all. Thanks for listening.